With this lecture, we begin the electronics section of the course. And the very first topic that we are going to tackle in this particular lecture is the PN junction diode. Now, most of you are familiar, at least in some form or the other, with the PN junction diode, its construction, its mode of action, and also some circuit applications. You have seen all of that in your high school course. We will primarily be recapitulating those results in this first couple of lectures. However, there are many aspects of the theory here which is rather complicated and subtle, and which, frankly speaking, requires a rather thorough knowledge of solid-state physics, quantum mechanics, statistical mechanics, in order to fully appreciate what is going on. So frankly, at this stage, I am not really in a position to explain the physics behind everything that I am going to say here. So what we are going to do is, in providing you with a background, we will assume the following information from solid-state physics. I am saying solid-state physics, but there are really things which come from solid-state physics, from quantum mechanics, from statistical mechanics, and so on. Some of these results you already know, although you may not know exactly where they came from, and some of them may be slightly new to you. Firstly, and this is a really magical result, which is this: if you are in a periodic potential, the kind that is found in a crystal lattice, the allowed electronic energies are not discrete levels with a big spacing between them, but they really form bands. This means that there are continua of allowed energies which an electron can be in, and then there are gaps in between. Now, how do these bands come about? Well, to understand this fully, you will have to solve the quantum mechanical problem involving the particular periodic potential that is there in a given solid. There are many toy models which help you to understand this. One of them is the Cronin-Penny model, which you may study in your quantum mechanics course this semester, or even if you don't, you will definitely study next semester or next year in solid-state physics course. Let me just give you a sort of hand-waving understanding as to where the bands come from. Because this is just one way of understanding bands. There are many different ways of thinking about the same thing. But let me just borrow your high school chemistry knowledge a bit. You know that when you have two isolated hydrogen atoms, say, they have energy levels which are identical, and there are gaps between those levels. Now, when you bring two hydrogen atoms very close to each other, these levels start to get modified because of the interaction with the other nucleus. And the effect of this interaction essentially is that, say, the two ground levels, if we focus on that, of hydrogen, they split into two levels, one slightly lower in energy, the other slightly higher in energy. These are the so-called bonding and anti-bonding orbitals that are produced in a molecule. But remember, you had two levels to begin with, that is, two levels corresponding to 1s for each atom, and because of perturbation they split a bit, but you still have two levels. Now, what happens when you have n atoms in close proximity? Well, you expect these levels to split into n levels. So each level from one atom, they essentially become n very closely spaced levels. And because the number of atoms is huge in a solid, the number of these levels is also huge. So you have a small energy spacing inside which there are many levels. So these levels essentially seem to be like a continuum. Of course, the original levels had a big energy gap between them, and despite the spread in the energy because of these perturbation effects which changes the levels a bit, there might still be gaps between the bands which are formed now. So the many levels, closely spaced levels that you have, they form a band, and the original gap between the levels, they survive in the form of energy gaps between these bands. Now you can make this into a formal theory, and the formal version of this theory is what is called the tight binding approximation in solid state physics. But that's just one way of looking at how bands are formed. There are other alternative ways. In fact, there are ways in which you start from almost exactly the opposite assumption. Here we assume that the electrons have more or less sort of property of their given atoms, and they interact among each other when the atoms get close. But you can come from an entirely opposite viewpoint where the electrons are essentially free and the effect of the nuclei from the atoms is really treated as a small perturbation on that. It so happens that both these models, though they differ in their quantitative details, they give you qualitatively very similar results, which gives us confidence that the ultimate result is sort of okay. So we have this band structure, which of course we know is true because experiments tell us this is true, but we can justify this using this kind of quantum mechanical argument, or when we learn a bit more, much more detailed calculations, these bands are a fact of life. So in a solid state crystal, what you have are electrons are there in energy bands with gaps in between. Now the electrons of course try to go to the lowest possible energy levels available. The problem is they are fermions, and because they are fermions, they cannot all crowd into the lowest energy level. So at absolute zero, when there is no other energy to excite the electrons fill up the allowed energy levels from the lowest one upwards. Now this leads to a situation that at the end there are a certain number of bands which are completely filled, and there are a few bands which are either completely filled or partially filled. Now if the highest occupied band is partially filled, the solid then is a conductor. Why? Because in a conductor, a solid must be able, and I say conductor I mean both electrical and thermal conductor. In a conductor, a solid must be able to respond to external fields, to a temperature gradient or to an electric field. Now, the way in which electrons can respond to external fields are by changing their state and going to a neighboring state. Now, if the highest occupied band is partially filled, then close to the level that an electron already occupies, there are other empty levels. Note that electrons being fermions, they cannot go to a level where there already is an electron. So you need empty states available for electrons to be able to change their state and hence respond to external stimuli. So if the highest occupied band is partially filled, at least the electrons near the top of that band or top of that half filled band, they have enough energy levels or empty energy levels available nearby for them to transit into and hence respond to external stimuli. So in this case, the highest partially occupied band is where all the conduction occurs. The lower bands, which are completely filled, have electrons which are essentially inert to external stimuli simply because they don't have any neighboring levels to jump to. The highest band is called the conduction band. Now if the highest band is fully filled, now we have either an insulator or a semiconductor. Now in this case, the terminology goes this way. The highest fully occupied band is called the valency band for this particular solid. So that's completely filled. And the next band is unfilled, empty at absolute zero. And this band is called the conduction band. And it is a gap which is there between the conduction band and the valency band which dictates this energy gap. This is what dictates the nature of the solid, whether it's going to be an insulator or a semiconductor. But before we discuss why that is the case, let us just step back a bit and learn a bit more of results which come from quantum mechanics. Now firstly, we have already said this. Being fermions, electrons can only respond to external fields if there are neighboring free energy levels. And as a result, if you have a half-filled level, you have a conductor, but fully filled bands are inert. Now in a periodic potential, and this is an amazing result from quantum mechanics, electrons behave like a free particle. Now you realize that this is, well, a miraculous thing. You have an electron which is not free at all, but it's in a periodic potential. It essentially behaves like a free particle. Well, not exactly like a free particle. The only major difference that occurs is that their mass changes to what is called an effective mass. So what that means is, if you put in an external field, the rate at which the electron may respond to that field, that will change, and that is really because of the effect of the periodic potential which is there. So this is a purely quantum mechanical result. There is no way to understand this particular result in a classical picture. But it comes out in a pretty straightforward manner from the application of quantum mechanics. And this is one of those results which I said we are going to assume for the time being to be true. In fact, if you think of a truly free particle, its energy is given by h cross square k square by twice m, p square by twice m, and p is h cross k. This of course means that you can write the mass, or rather the reciprocal mass, in terms of the second derivative of energy with respect to k. Well, if you have a periodic potential and then put an electron in that, the electrons will form different bands, and in each band you have a different relationship between energy versus the wave number. Ek relation changes from band to band, and this of course, the details of this relationship, that depends on the nature of the particular periodic potential. So that of course changes from solid to solid. And one more thing, E of course depends in this case not only on the length of the wave vector k, but on all the three components k1, k2, k3. And as a result, you end up, instead of mass or a reciprocal mass, as in this formula, you end up with something called a reciprocal mass tensor. That may sound complicated, but that essentially means the electron can behave differently when it's moving in different directions. And that's simply because the periodic potential may of course be different in different directions. Now, we will not need the details of all this in the rest of the lectures. However, just for completeness, let me just write down that the effective mass for an electron, if you know the E versus K relationship, is pretty easy to figure out. It's just an analog to this equation for the free particle. Instead of the second derivative with respect to K, you end up with the partial second derivative with respect to Ki, Kj, and you end up with something called 1 by Mij. If the band is isotropic, the same in all directions, then you again end up with a single effective mass. The value of the effective mass depends on del 2 E del K2, which in general will depend on K. So the electrons within a given band will behave as if they have different masses depending on their wave vectors. Now, and this is all that we will really need from this story about effective masses, near the bottom of a band, energy of course is close to a minimum. And there, of course, the second derivative will be positive, and so the effective mass is positive. Now that's great. It's a mass after all, it should be positive. But near the top of the band, E actually is near its maximum. At the top, it really is maximum. And the second derivative of a quantity, it attains a negative value at its maximum. And that means that near the top, the effective mass of the electron is negative. Now this may sound like a strange and unusual result, and it is. But what does a negative mass really mean? It simply means that if you give an electron a force in a given direction, it's actually going to accelerate in the direction opposite to it. That is really strange, but if you think about it a bit, the electron is not really responding to the external field that you are producing, it's also responding to the effect of all the other forces due to the nuclei which are already there. They are part of this periodic potential. So what the periodic potential has done is that it has conspired to make the electron accelerate in the direction opposite to the external force. So the final result of this entire periodic potential is actually so simple, it just changes the mass and does nothing else. That is one of the miracles of quantum mechanics. But once you take that for granted, there is no escape from the fact that electrons near the top of a band behaves like a negative effective mass particle. And as we will soon see, this is something which we actually need going forward. Well, let's come back to pure insulators and semiconductors. And note the word pure. When I say pure, I mean, well, I don't mean absolutely pure, because no sample can really be absolutely pure, but I really do mean of very, very high degree of purity. So for such samples, at absolute zero, there are no free charge carriers at all. All the charge carriers are in fully filled bands and they will not participate in conduction. So at absolute zero, both insulators and semiconductors are insulators. They don't conduct. But once you raise the temperature a bit, at a finite temperature, a few electrons near the top of the valency band gather enough energy to cross the band gap. So what happens now? Now you have electrons in the conduction band. Now note that they are near the bottom of the conduction band and there they behave like positive effective mass particles. Negative charge positive effective mass particles. Electrons, for all we care, except that their masses are not that of the free electron. That's something which is dictated by the E versus K relationship there. So those are our conduction electrons. On the other hand, what we also have is the valency band is now not completely full. A completely filled band would be inert to external influences, but now you have a few gaps left behind by the electrons which have left for the conduction band. Now these gaps are gaps of negatively charged particles which had negative mass. Remember, these electrons were near the top of the valency band and there their effective mass is negative. So their absence essentially behaves like positive charged particles with positive mass. Now you have learned about holes. So these are exactly what are called holes, and you have learned about holes in your class 12, and then you have learned about the fact that holes are gaps left behind by electrons. So because they are gaps left behind by negative electrons, they are positively charged. What you may not have realized is that you need the electrons whose gaps these are to also have negative mass in order that holes really behave like positive charge, positive mass particles. But that is exactly what electrons behave like near the top of the valency band, and the gaps really behave like positive charge, positive mass particles, which we call holes. So this hole is nothing but a gap in an otherwise filled valency band, and because the full valency band is neutral, a gap essentially behaves like a particle with exactly negative properties. Negative of the negative charge, negative of the negative mass particle. So holes behave like particles with positive charge and positive mass. Now, since this conductivity that you have now is because of the fact that there are holes in the valency band, the gaps in the otherwise filled level, so you can have conduction there. You also have some electrons in the conduction band, and these electrons have neighboring levels which are completely free, so they can respond to external stimuli. So now you have conductivity. And where does this conductivity come from? It comes from the formation of electron-hole pairs, which essentially comes because of the energy provided by thermal fluctuations. Raising the temperature, of course, increases these pairs a lot, and so the conductivity of such samples rises with temperature. This is in stark contrast with what happens with metals. In metals, you already have plenty of electrons which are freely available to conduct, and raising the temperature essentially creates impurities in the metal crystal, and these impede the motion of these electrons. So in a metal, the conductivity falls with temperature. In insulators and semiconductors, on the other hand, conductivity rises. Now this effect, this conductivity, is very, very small if the gap between the valency band and the conduction band is rather large, much bigger than 1 electron volt, say 10 electron volts or nearabouts. and then we have an insulator. On the other hand, if the gap, this band gap is tiny, of the order of 1 electron volt or less, then even if you raise the temperature by a small amount, you are going to get a reasonable amount of conductivity. And this conductivity, which has this startling feature of increasing with temperature in contrast with a conductor, is what characterizes the sample as a semiconductor. So an insulator has a large band gap. A much smaller band gap is what gives rise to a semiconductor. Of course, the number of holes and electrons increases with temperature. In fact, increases exponentially with temperature. And for intrinsic semiconductors, that is semiconductors which are completely pure, the kind we are talking about here, the number of electrons and the number of holes, even this small ni and small pi are actually concentration of electrons and holes. These are both equal because they are of course produced together. The concentration is what I call M0 here, and M0 depends only on the temperature. It's actually a rather sharply increasing function of the temperature. So this is one fact you have to keep in mind. Electron hole pair formation because of temperature increases rapidly with temperature. This is going to be crucial in order to understand various features and problems with semiconductor devices. Well, now we move on to what really makes semiconductors useful. Pure silicon and germanium, for example, are examples of intrinsic semiconductors. These are materials for which the band gap between the valency band and conduction band is of the order of 1 electron volt each. 1 electron volt roughly for silicon and a bit less for germanium. And now comes this really funny thing. If you dope very lightly with the pentavalent impurity, pentavalent means you have one more electron in the outer shell than the silicon or germanium which makes up your basic material. If you dope it with a very small amount of pentavalent impurity taken from the same period, this is important because if two atoms belong to the same period, they have roughly the same size, which means a pentavalent impurity can displace or can take the place of a gap left behind by the absence of an atom in the original solid. If you have taken an atom pentavalent impurity from some other period, the size may be too big or too small. If it's too big, it may distort the crystal lattice and change the behavior. If it's too small, it may make the crystal lattice cave in. If it's like Goldilocks, not too big, not too small, just right, it sort of fits in right there. And if you remember your class 12 picture, it bonds with 4 of the neighboring atoms and has one electron free. In the band gap picture, you describe the same thing slightly differently. If it's a pentavalent impurity atom, it essentially ends up having one level which is very close to the conduction band, otherwise empty conduction band. So it's very easy for these electrons to jump into the conduction band, giving rise to conduction electrons. Now notice that these conduction electrons come in without any corresponding holes because the electron hole pair formation has not occurred here. So in an intrinsic semiconductor, the number of electrons and number of holes are always equal. If you dope a semiconductor with the corresponding pentavalent impurity, you end up with more electrons, more free electrons. When I say electrons and holes, I always mean electrons in the conduction band, which are free to move around, and holes, of course, are gaps in the valency band, which are also, in a sense, free to move around. So now you have more electrons than holes, and you end up with what is called an N-type semiconductor. Well, instead of a pentavalent impurity, if you try a trivalent impurity, this leads to a P-type semiconductor. Again, a fact which all of you know. And once again, you have to take a impurity from the same period in order to sort of not disturb the crystal lattice too much. Also, the doping has to be very light so that you do not disturb the crystal lattice too much, and so on. So a p-type semiconductor, in the band picture what happens is the trivalent atom provides an energy level which is close to the top of the valency band, which is otherwise empty. And so now electrons from the valency band can jump onto that empty level, not exactly at absolute zero temperature, but at a temperature very close to absolute zero, slightly higher than absolute zero. The electrons can make the jump from the top of the valency band to these empty so-called acceptor levels. And now you have gaps in the valency band, holes, without any corresponding conduction electrons. So now you have more holes than electrons and you end up with a p-type semiconductor. One thing is very important. The number of electrons times the number of holes must stay a constant in this process. That's simply because electrons and holes being bonded together, and so essentially not being there at all, to pair production producing electron hole pairs, this is a reversible reaction. And np equal to n0 square, you can call that Le Chatelier's principle, law of mass action, or simply chemical equilibrium. No matter which way you look at it, it essentially says that since electrons and holes can go in each direction, they can either bond together to destroy themselves or break up into electron hole pairs, the product has to stay fixed. And it also means that if you are in an n-type semiconductor where you have more electrons produced because of the donor impurity giving more electrons, the number of holes is going to be less than in the corresponding intrinsic picture. Similarly, in the p-type semiconductor, you have more holes and that suppresses the electron hole pair formation. You end up with less electrons. So for an n-type semiconductor, the number of electrons is roughly equal to the number of donor atoms. Why? Because it's the donor atoms which produce the bulk of the electrons here, and the number of holes is suppressed. It's not equal to, is definitely not equal to the number of electrons. It's not equal to n0, the number of both electrons and holes. In the intrinsic case, it's actually n0 squared divided by nd. So you have many more electrons and almost no holes. And very often what we will do is we will say that an n-type semiconductor has conduction electrons. Remember, when I say electrons, from now on I always mean conduction electrons, electrons which are in the conduction band, which can take part in conduction. Electrons which are bound to the nuclei are really as good as not there for us. Similarly, for a p-type semiconductor, the number of, or the concentration of the holes is equal to the number or the concentration of the acceptor atoms. And this is a typo. This should be n should be pz n0 square by na. So this is of course wrong. Holes concentration depending on how many acceptor atoms you have put in. Electron concentrations going down as a response. Now notice that in an intrinsic semiconductor you have as many electrons as holes. So charge neutrality, that's not a problem. You have electrons which are negatively charged, holes which are positively charged, which balance each other out. What happens in a n-type or a p-type semiconductor? Now you have more electrons, for example, in an n-type semiconductor. So is the n-type semiconductor negatively charged? Of course that's impossible, right? Because how did you create an n-type semiconductor in the first place? You took an electrically neutral intrinsic semiconductor, doped it with a pentavalent impurity, which also was electrically neutral. So where would the charge come from? The answer, of course, is that an n-type semiconductor is not negatively charged, it's neutral. It has more electrons, but it also has a bigger positive core charge which the nucleus, which the pentavalent impurity has brought in. So for each electron with a -1 charge, the pentavalent impurity has a corresponding +1 charge. So the overall charge neutrality is maintained here by the fact that you have donor impurity atoms. For a p-type semiconductor, you have holes positively charged, they are in excess, but the acceptor impurity atom has one charge less in the nuclear core, which means the acceptor impurity atom effectively behaves like a minus or negative charge. Once again, charge neutrality is maintained. But this is very critical. Charge neutrality between conduction electrons in one case and holes in the other is maintained by the donor atoms in one case, the acceptor atoms in the other. But in both cases, the impurity atoms are immobile. They are stuck to where they are in the crystal lattice. They will not be able to move, whereas the electrons and holes can move. This is critical to understanding the behavior of various devices made out of extrinsic semiconductors. And it is one such device, the PN junction diode, that we are going to talk about next. We will now discuss the simplest of the non-trivial devices you can make using semiconductors. This is a PN junction diode. So we will discuss the properties of the PN junction now, and as you will see that this is going to lead to the formation of a device called a diode. Now oldies like us remember that in the good old days of electronics, well, way before we were born to be more precise, the roost was ruled by something called a vacuum diode, which essentially was a bulb which was completely evacuated, had two electrodes, a cathode and an anode, and the cathode was heated. Because the cathode was heated, it could emit electrons by a process called thermionic emission. And now the situation was very simple. If you made the anode positive with respect to the cathode, the electrons could flow because of the attraction of the positive anode to the anode, establishing a current in the circuit. If on the other hand you made the anode negative with respect to the cathode, the electrons were repelled and they could not make it onto the anode, hence no current. So vacuum devices, and there were more based on further electrodes put in and other clever stuff that you did, were really very easy to understand. They just worked on the basic principles of the fact that when you heat a metal, they emit electrons, at least some metals do, and the rest is just Coulomb's law. Like charges repel, unlike charges attract. Of course, the PN junction diode, as we will see, behaves in much the same way. You will find that current will essentially flow in only one direction through a PN junction diode and not in the other. The mode of operation of a PN junction diode, however, is much more complicated than the corresponding vacuum diode scenario. For a vacuum diode, all you had to worry about was standard laws of electrostatics. The reason why we don't use them very often now, although we still use them in specialized situations, is not that they were difficult to understand, but they were difficult to work with. They were bulky, they needed a lot of power, they could heat up a lot, and so on and so forth. The PN junction diode has really revolutionized electronics for us, and so the extra amount of effort we have to put in to understand how it works is well worth it. And as you will see, at least understanding the basics of how it works is not that difficult. Once again, this is something which you may have already learned at least in outline about in your high school courses, but there may be a few subtle points, some of which I'm going to just gloss over because we don't know enough background physics to handle all the subtleties, but you will see that much of the behavior can be understood using very simple physics. Well, how is a PN junction diode formed, or how is a PN junction built? You essentially start with a pure N-type silicon or germanium wafer, thus this grey block that I have drawn on the left hand side. You could have also started, by the way, with a pure P-type. By the way, how do you produce a pure N-type silicon wafer? You start with very pure silicon. Producing that in itself is an industrial challenge. And one major way in which this is produced is that you put the silicon wafer for a controlled amount of time in a vapor of pentavalent impurities. So what would happen is that this silicon wafer or silicon crystal will have some amount of imperfections in it, some gaps where there should have been silicon atoms but there aren't, and the pentavalent impurity atoms would diffuse through the crystal and go and sit in those locations. How strongly are you doping? That can be controlled by both the density of the vapor that you use, also the time of the exposure, and all of this is a very critical industrial challenge to be able to do this in a very nice controlled fashion. But well, because we are just learning the theory of this, we can be glib and say all you do is take a piece of silicon wafer, put it in some pentavalent impurity vapor, and that vapor permeates inside and you get an N-type wafer starting from an intrinsic wafer. Then what you do, you cover up most of the surface of this silicon chip, leave a small bit exposed. How to do that in itself is a rather important industrial challenge, but all this can be done nowadays with relative ease. And then you expose the exposed portion of the chip or the wafer to a trivalent impurity vapor, again in a controlled amount, so that ultimately you manage to deposit a p-type region inside the n-type wafer or n-type substrate. So a junction is usually formed by growing a p-type layer inside an n-type chip. However, to understand the way in which a p-n junction works, we will make use of a fiction that you are really creating a p-n junction by taking a p-type semiconductor, a pure p-type, a pure n-type, and just putting them together. That's not how a p-n junction diode is usually produced, and one of the major reasons is if you take two distinct wafers and you try putting them together, there will be too many gaps at the interface for the thing to work properly. You need the gaps to be near zero at even the atomic level, and that requires a huge amount of precision, which would make the whole process extremely expensive. So nobody really produces p-n junctions the way we are going to describe next. But let's imagine that I have a p-type wafer, an n-type wafer, two blocks of semiconductor, one p-type, one n-type, and their faces are extremely smooth, so smooth that I can put them together in such a way that the gap between atoms really come out to be at the atomic level, gap between the surfaces. And if we can manage doing that, we get a picture like this. Okay, I have drawn an n-type semiconductor on the left and a p-type on the right. The n-type semiconductor, of course, has lots of electrons, free electrons, which are these blue dots here. This is just a cartoon picture, of course. Don't go and imagine that electrons really are blue dots in a yellow background. And of course, they are not placed are not situated so regularly inside the crystal as well. But this is just a cartoon picture to make you understand what's going on. On the other side, you have holes, which are these red dots. Now, you have to remember that despite the presence of these electrons on the n-side, the n-side to begin with is electrically neutral. Why is that? Because the background consists not just of neutral silicon or germanium atoms, but also of the donor impurity, which has +1 charge. So here I've indicated the yellow tint here to be the neutralizing positive charge, which is spread out all over the material. Similarly, on this side, the green here, or the lime green color here at the background, that's the charge provided by the acceptor impurities, uniformly distributed throughout that particular wafer. Okay, this is the picture before you put the p and n type together, and now you just bring them together. What will happen? Well, you have an excess of electrons on the left of this picture, excess of holes on the right, and both electrons and holes are free to move. So what will happen? Well, what will happen is what happens when you, say, put a drop of ink in a glass of water. You have a high concentration of ink in one region more ink in the rest. So what will the ink do? Because of random molecular motion, you will have diffusion. So electrons will diffuse from the N type to the P type, while holes will diffuse in the other direction. So you will have some blue dots, the electrons, crossing over to the P side, some red dots, the holes, crossing over to the N side. Of course, diffusion is random, it should happen in all directions, but the gradient of electrons is such that the diffusion will occur primarily from the N side to the P side for electrons and from the P side to the N side for holes. Now, if you think about the diffusion of ink in water, this may take a long time, but in time what will happen is that ink will diffuse all over the water and you will be left with a uniform ink-water mixture. The same does not happen here, thankfully, because if the same thing had happened here, you would have ended up with all the electrons and holes diffusing all over the place, of course meeting each other and killing each other by recombination in the process, and ultimately you will be left with either an intrinsic semiconductor effectively, or maybe an N type or a P type, depending on which particular side was doped more. But that would be rather uninteresting. All this trouble that you're going through of creating a P type and an N type and putting them together is simply wasted, or would have been wasted if this were to happen. There is one big difference in this situation and the situation with ink in water, and that is that electrons and holes are both charged. So when they move over from one side to the other, they carry their charge with them. Remember, the overall N-type semiconductor to begin with, or the P-type semiconductor to begin with, they are both neutral. Why? Because in the N-type semiconductor, you have donor impurity atoms, which were neutralizing the electron charge. On the P side, they were acceptor atoms, which were neutralizing the hole charge. As I have stressed before, electrons and holes can move, but their neutralizing agents, the impurity atoms, cannot move with them. So when the electrons shift from the N side over to the P side becomes negative as a result. Similarly, when holes diffuse from the P side to the N side becomes positive. And this gives rise to a potential barrier. So N side here becomes positive, as is indicated by the red pluses here, and the P side becomes negative. And this potential barrier makes it more difficult for the electrons and holes to diffuse. Why? Because in order to diffuse, the electrons and holes will have to now overcome this extra potential which is preventing or trying to prevent them from diffusing over. So this causes the diffusion to slow down. And what happens as a result is right next to the junction, electron holes recombine, they have crossed over, they recombine, and they produce a region which is free of any free charge carriers. That is, you don't have electrons on this side because they have been killed by the holes which have come in. Similarly, the holes here have left, and whatever was left after the holes diffusing have been killed by the electrons coming in. So you have a region where there are no free charge carriers on both sides of the junction. This is called a depletion region. Now, of course, on the P side, as we said, holes leaving behind the acceptor ions. Hence, this region becomes negatively charged. So that's the minus sign here. On the other hand, the depletion region on the N side has an excess of donor atoms and no electrons to cancel the charge. So depletion region becomes positively charged on the N side. As a result of this, now you have an electric field directed from N to P, from the positive charge to the negative charge, all over the depletion region. And this electric field is now trying to prevent holes from crossing over from this side to that side. Also, electrons from crossing over from this side to that side. Holes being positively charged feel a force in this direction towards the right. Electrons being negatively charged feel a force in this direction to the left, away from the junction in both cases. And it is this electric field which gives rise to the potential barrier, and it's this potential barrier which makes it difficult to find electrons or holes which have enough energy to still jump across. So diffusion current decreases rapidly once this potential barrier is formed. Decreases, but doesn't go to zero, because after all, no matter how big a potential barrier you have, there will still be some electron or some hole with enough energy to surmount that. So the electric field here, this internal electric field across a junction, plays a rather strange role. Instead of helping current to flow, it actually prevents or lowers the diffusion current. But suppose you have an electron here on the p side. Now why should you have an electron here any longer? After all, I said the depletion region has no charge carriers. But remember, electron hole formation because of thermal effects are going on all the time. So from time to time, an electron hole pair will form here on the p side, also here, and so on. Now, if an electron hole pair is formed deep inside the n-type semiconductor or deep inside the p-type semiconductor, they may drift around a bit, but before moving very much further, they will meet. The electron hole pair will have an electron. The hole will move around a bit and then meet one of these electrons and kill itself, leaving the number of electrons the same as before. So that really is not going to contribute anything to the picture overall. But an electron hole pair formed here is a different story. Suppose an electron hole pair is formed in the depletion region, let's say on the n-side, just to be specific. So the hole is pushed by the electric field to the right into the p side. So the hole is made to cross over. Electron, on the other hand, is pulled in the opposite direction, but same electric field, but the negatively charged particle. So electron gets pulled back. So both of these go out of the depletion region because of the electric field. So the moment a pair is formed anywhere in the depletion region, the electric field actually sort of drives it out of the depletion region. But notice the electron has not crossed the junction, so it's still on the n side, but the hole has crossed over. So what has happened? You end up with a current across the junction because of the electric field. So this is a current which is produced by an electric field which is pushing the charge carriers along. Now this, again, if an electron hole pair to form here, the hole will be pushed in this direction away from the junction, but the electron will be pulled into the n side, crossing the junction. Of course, in both cases, with the hole crossing over to the right or the electron crossing over to the left, you get a net current towards the right. This current is opposite in direction to the diffusion current. In diffusion current, holes were diffusing to the left, electrons to the right, both leading to a diffusion current which is pointing to the left. The drift current, on the other hand, is just in the opposite direction. It's caused by the electric field which is there, and it essentially pushes electrons or holes which are produced in the depletion region for thermal reasons across the junction. Now, in the absence of external bias, these two currents, diffusion and drift, must cancel, so that there is no net current across the barrier. How does this happen? Let us just take a look at that in some detail. Notice that the diffusion current must decrease exponentially with the size of the barrier potential. The higher the barrier potential, the more difficult it is to find electrons or holes with enough energy to cross the barrier. And as you may be aware from elementary knowledge of statistical mechanics or some thermal physics that you have already studied in your previous semester, the larger the energy is, the probability of finding a particle with such an energy becomes exponentially lower. So this is why the diffusion current falls off exponentially with the barrier potential. So JDI is the current density due to diffusion. Unfortunately, diffusion and drift both start with a D, so I could not write JD. So the diffusion current is of course towards the left, and as we have already discussed, the drift current produced by the electric field is to the right. Now, as long as the diffusion current is larger than the drift current, and in the beginning, of course, the diffusion current is all you have. The drift current kicks in only once the diffusion leads to the electric field being formed in the first place. So initially, of course, diffusion current is larger, drift current is negligible. Then the electric field kicks in, you have a drift current, the diffusion current comes down. But as long as the diffusion current is larger than the drift current, there will be diffusion and the barrier will keep on increasing. And this will ultimately bring the diffusion current down to a situation where the diffusion current exactly balances out the drift current. And once that happens, you have a steady situation. Here we have not connected any battery or any source to the PN junction, and what we have is the drift current and the diffusion current balance each other out exactly. So JDR is negative of A e to the minus ED by kBt. Now this is the situation without any bias. If you imagine just joining the P and N type together, initially there will be big diffusion, but once diffusion occurs, electric field will set in. That will make diffusion harder, so diffusion will go down. But as long as diffusion is bigger than drift, the barrier will keep on growing, making the diffusion further more difficult, and ultimately there will be an equilibrium situation where there will be no net current any longer. So that's easy enough to understand. What happens if you were to now connect a battery in such a way that the N side, the one on the left, becomes positive and the P side becomes negative? So what I'm doing is I'm actually aiding the barrier potential here. I'm making the barrier potential even bigger. And what happens now is that the depletion region becomes wider, the barrier potential becomes bigger, so the number of pluses here, if you paid attention, has grown a bit. And that causes JDI, the diffusion current, to fall. What happens to the drift current? The drift current actually stays almost the same. Now why is that the case? It might seem, of course, that the drift current is caused by the electric field. This bigger barrier means larger electric field, so shouldn't the drift current also increase? But remember, the drift current is essentially crossed by holes on the N side, or more strictly, holes produced in the depletion region inside the N side, the minority charge carrier there, crossing over, or electrons on the P side crossing over. In an extrinsic semiconductor, the number of minority carriers is very, very low, even much lower than that in an intrinsic semiconductor. So the drift current is primarily limited by the number of minority carriers present. Once you have some amount of electric field, that's enough to drive all the minority carriers to one side or the other. As a result, further increase in the electric field does not really increase the current. Here the current is essentially limited by the rate at which the minority charge carriers are being produced. So the drift current stays more or less the same. Of course, this is a result assuming temperature stays the same. If you raise the temperature, pure production rate will rise rather rapidly and the drift current will change. But we are saying at a given temperature, the drift current more or less stays the same. So I have shown a smaller diffusion current here, but almost the same drift current. Now if you increase the potential, the reverse bias a bit further, even by a small amount, the depletion region becomes even wider. But before that, just let's take a look at the equation here. The net current is now a sum of J drift, which is the same as before, and J diffusion. But J diffusion now is no longer A to the minus ED by kBt, which remember was just cancelling J drift, but you have an additional plus V here, which means the diffusion current is even smaller in magnitude. So it does not cancel J drift fully. And if you increase the inverse bias V even more, the depletion region widens more, the diffusion current becomes even smaller. It was so much smaller that it becomes negligible compared to J drift, and so you're left with almost J drift being the entire current. And this is a very, very tiny current, despite this big arrow that I've drawn just for illustration purposes. Remember, the drift current is completely controlled by the amount of minority charge carriers that can be produced within the depletion region by this electron hole pair production. That's much, much smaller than the current that's otherwise possible in an extrinsic semiconductor. So you have a very tiny current flowing in the direction of the potential, right? It's flowing from positive to negative, and but it's very, very small. So unlike a vacuum diode, where if you were to make the anode negative with respect to the cathode, you get no current whatsoever, or here you do get some current, but that current is very tiny. Well, actually, even for a vacuum diode, you did get some current. Some electrons were adventurous enough to still overcome the repulsion of a negative anode and get to the anode, but that number was much, much lower than the minority current here. So a reverse bias diode does carry some current, a very tiny amount, but still is there. And you have to also remember one very important thing, which is this minority carrier current actually grows with temperature, and that's going to be critically important in some applications, as well as a source of major annoyance in some devices. But now let us look at what happens if you were to reverse the battery, or rather forward the battery, so to speak. That is, you connect the battery so that the positive end of the battery is connected to the P side and the negative end to the N side. Now you are actually opposing the barrier potential. EB falls to EB minus V, where V is the battery potential, and that makes the depletion region shrink, the barrier potential to go down, and the diffusion current increases exponentially. Once again, this does not affect the drift current too much. The diffusion current increases exponentially as a result. So now you have J drift, which was still the same as before, as a contribution to J, but in addition you have A to the minus EB minus V by kBt. And just to remind you, A to the minus E by kBt is exactly minus J drift, or mod of J drift, assuming that this is what I am going to call the positive direction of current. And if you take that into account, this formula becomes mod of J drift e to the power plus V by kBt minus 1. So finally what we see is that if you forward bias a diode, that is, you connect the positive end of your battery to the P side and the negative end of your battery to the N side, you will get a large current flowing in, and that current is going to sort of exponentially increase with the battery potential. So this of course shows two things. One, reverse biasing the diode, trying to make current go from the N to the P, leads to a very, very tiny current. This tiny nature of the current is what we approximate often by saying the diode does not conduct any current in the reverse direction. Well, in a typical well-constructed diode, this tiny current can be anywhere from a fraction of a microampere to a few nanoamperes, a very tiny current. And the other thing is, when you forward bias a diode, you get a current exponentially depends on the voltage. And very soon what happens is this factor becomes very large and the minus 1 is negligible compared to that. So the current in a diode increases exponentially with the voltage. So this is a clear-cut case of a non-linear circuit device. Not only does it conduct in only one direction substantially, the current increases not in proportion but exponentially with the voltage. Now this is a rather crude picture that I have painted here. There are many other subtle things which go on inside a diode, and if we wanted to really design a diode for best performance and so on, we would have to understand all these other physical phenomena that's going on here. And this is really the subject of device physics. But right now we are not going to go into the details. We have just used elementary physics to understand how a PN junction diode works and why is it that it conducts a lot more in one direction than in the other. And next day we are going to start with this and describe how to use a diode in a circuit context. That's for the next lecture.